Hi, everyone. So in this video, we will be continuing our discussion on sequences. At the end of the last video, we talked about how a lot of our sequences problems will be dealing with finding the nth term, or the term that's written in the nth position of our sequences. So we're going to start by looking at our first numerical sequence today. So whenever we're analyzing sequences, one thing that we can do to help organize our work is to create a table. So using one of our strategies from section 1.1. So for each n, we're going to have a different, that's kind of crooked. So for each n, we're going to have a different term in our sequence. And from that, we can try and find a pattern. In our pattern, we want it to be in terms of n, because like we said before, we want to find this nth term of the sequence. So we want to be able to find a pattern so that when we plug in n, we know exactly what the term is going to be. So we want this pattern to be in terms of n. So in terms of n, just meaning an expression that has n as the variable. So we are given the first 4 terms in this sequence. So the first term is 7, the second term is 18, the third term is 29, and the fourth term is 40. And so we want to figure out what the pattern is. So just looking at these terms, we have some that are even, some that are odd. We don't have anything in the 30s. So let's think back to some of the patterns that we recognized in section 1. So in section 1, one pattern that we dealt with was Pascal's triangle, where we added different things. So let's see what happens with adding if we look at adding different things to these terms. Well, we can see that going from 7 to 18, we add 11. To get from 18 to 29, we also add 11. And to get from 29 to 40, we also add 11. So we add the same thing to our term every time to get the next term. So now let's see how we write that in terms of a pattern. So we have that 18 is 7 plus 11. We have that 29 is 18 plus 11, and 40 was 29 plus 11. So now remember, we want this pattern to be in terms of n. So we want these expressions to look similar with only one thing different, which is going to be our n value. So instead of adding each number to 11, because remember, we want to have the nth term of the sequence down here, and we want to be able to plug in n into our pattern and know exactly what term we're dealing with. So let's change these a little bit. So our second term, we have 7 and we add 11 once. So now to get to our third term, instead of writing it as 18 plus 11, we can write it as 7 plus 11 twice, since we went down from 7 down to 18 and then down to 29 again. So we added it twice. And so now to get to our fourth term, we started at 7 and jumped down and added 11 3 times. So let's simplify these a little bit. So instead of adding 11 twice, we can write it as 7 plus 2 times 11. And then for our fourth term, we can instead writing it as 7 times 3 times 11. And in order to keep this pattern consistent through the terms, we can rewrite this one up here as 7 plus 1 times 11, and our first term as 7 plus 0 times 11, because anything times 0 is 0, and anything plus 0 is itself. So 7 plus 0 times 11 is still 7. So now we can get a general pattern, because we need something that we can plug in our n value and get the term. So we need a pattern where things are fixed, but only one thing changes. So the only thing that changes in these expressions is how many times 11 is added to 7. So we go from 0 to 1 to 2 to 3, increasing by 1, just like how our terms go 1, 2, 3, 4, increasing by 1. So we can write our pattern as 7 plus, so we don't multiply by our n value, but 1 less than it, 7 plus n minus 1 times 11. And so that is our general form. So any sequence like this, where the difference between the terms is some constant value, so we either add or subtract a fixed number to each of our terms, that is going to be called an arithmetic sequence. So an arithmetic sequence. And so these are always going to have this form as our first term. So we have a general form where we have our first term plus n minus 1 times our constant. So this is going to be our constant that we add to each term. So every arithmetic sequence, arithmetic for arithmetic for adding, is going to have this general form where our pattern is going to be the first term plus n minus 1 times the constant that we're adding each time. So this is going to be an arithmetic sequence. So arithmetic, you can always think of adding, is an arithmetic sequence, is always adding. And so we can see that this is true no matter what sequence we have, no matter what our first term is, no matter what our constant term is, this will always be the same. Okay, so that is our first type of sequence, is an arithmetic sequence where we add a constant between each term. So now we're going to look at our second type of sequence. So we're finding the nth term in this new sequence. So just like before, we're going to set up a table where we have n. Oops, let's crooked again. So we have n, the term in the nth position, and again, we're going to find a pattern that is in terms of n. Okay, so again, we are given the first 4 terms in the sequence. 1, 2, 3, 4. And then we're going to go all the way down to n. Okay. So our first term in this sequence is 2. Our second term is 6. Our third term is 18. And our fourth term is 54. Okay, so let's try what we did before. So we can try to see if we can add the same constant between each of our terms. So when we try that, we see that 2 going to 6, we add 4, and 6 going to 18, we add 12. So we can already see in these first 2 jumps that we don't add the same constant. So let's see what the pattern really is. Okay, so just like our example from section 1.1, right? We had Pascal's triangle, which was adding, but the example that we looked at in the video change that adding to multiplying. So let's see if that we can do the same thing here. So to get from 2 to 6, we multiply by 3. From 6 to 18, we also multiply by 3. And 18 to 54, we also multiply by 3. So we multiply by 3 each time. Okay, so this is a pattern that works. So now we just have to figure out how to write it. So just like before, to get 6, we do 2 times 3. To get 18, we do 6 times 3. But again, we want all of our patterns to look as similar to the one above it as possible. So this is really 2 times 3 times 3, which we can write just by combining the 3's as 2 times 3 squared, where 3 squared is just 2 copies of 3. And 54 has 18 times 3, but this is just 18 is 2 times 3 times 3 times 3, because we had 3 jumps down from 2 to get to 54. So this can be written as 2 times 3 cubed. And so just because we need everything above it to look the same, we can write 2 as 2 times 3 to the first, and 1, where 2 can be written as 2 times 3 to the 0. Remember that anything raised to the 0 is 1. So we need to remember that 3 to the 0 is 1. So this is our pattern. So now we want to write it for the nth term in the sequence. So all of these start the same, multiplying 2 times something else. But now we want to identify what changes in each of these, and that's the exponent. We start with 0, 1, 2, 2, and 3. So just like before, they increase by 1. So the first term is raised to the 0 power, the second term to the first power, the third term to the second power, and so on. So we can write this as 2 times 3, and the power is now n minus 1. So we have our pattern. So if we plug in any n, we can find out what that term is by plugging it into this expression. So this defines a different type of sequence called a geometric sequence. So you can see that this form is really similar to the arithmetic sequence. So this one also has a general form where we start with the first term, and instead of adding, we multiply by the 3 is called our ratio, and we raise it to the n minus 1 power. So it's really similar to our arithmetic, right? That one we had a general form where we did the first term plus our constant, which I guess we could also call our constant our ratio, our adding ratio. And then we come down here to the geometric sequence and we multiply, and instead we raise the ratio to a power. So these are our first two types of sequences, arithmetic and geometric. So these are pretty important. They'll come up, and you need to be able to identify these types of sequences by their general form and construct a general form when you see either of these types of sequences. Okay, that is all for this video.